In this lecture, we will study the effective mass of the electron. We know that electron has well-defined mass, and when accelerated by electric field, it follows Newton's law. Now, question arises, what happens when an electron inside the crystal is accelerated by an electric field? Now, its answer is, when an electron inside the crystal is accelerated by an electric field, its mass will differ from the mass of free electron. Mass of the electron inside the crystal will be different from the mass of free electron, and that is called effective mass of the electron. Mass of the electron. Now we know, according to de Broglie, every particle is associated with a wave. But quantum mechanically, Schrödinger modified this statement that every particle is not associated with a single wave, but group of waves. And those group of waves, when superimposed on each other, they form a wave packet or envelope. Wave packet or envelope. Now, the velocity with which this wave packet or envelope moves is called group velocity, Vg. This group velocity is equal to particle velocity, that is proved in my lecture, that is on group velocity and phase velocity and relation between them. Now, we can show that this group velocity is equal to velocity of the electron or particle velocity. So this is equal to d omega by dk, where k is propagation constant or wave number, omega is angular frequency, or you can say this is 2 pi nu. We know E equal to h nu. Now multiplying this by 2 pi and dividing by 2 pi, we get h cut omega. This 2 pi nu is omega, and h upon pi, this is h cut. So we get E equal to h cut omega. Now differentiating this with respect to k, we have dE by dk equal to h cut d omega by dk. Now from here, d omega by dk equal to 1 upon h cut dE by dk. So this is group velocity, and we see here V equal to 1 upon h cut dE by dk. This is velocity of the electron, and you can see here that velocity of the electron depends upon the slope of E versus K diagram. In last video, I have shown the E versus K diagram. And from there, velocity V is proportional to slope of this E versus K diagram. We know for free particle or free electron, you can say E equal to h cut square K square upon 2m. Now we will put the value of dE by dk from this equation. So differentiating it with respect to k, dE by dk equal to h cut square upon 2m into 2k. 2 cancel and we get h cut square k upon m. This is dE by dk. Or you can say 1 upon h cut dE by dk equal to h cut k upon m. So putting the value of 1 upon h cut dE by dk in equation number 2 from number 3, we have V equal to h cut k by m. Now this h cut k equal to p momentum we can show here. H cut is h upon 2 pi, k is 2 pi by lambda and into m from here 2 pi cancel, so we get h upon m into 1 upon lambda and lambda is h upon p, so we have V equal to p by m. So we can see from here p is varying linearly with k. There is linear variation of V with k, and V is also depending on the slope of this E versus K diagram. So we can show the variation of velocity versus K with the help of E versus K diagram, because velocity is depending on slope of the E versus K diagram. So from here we can show that at the bottom of the band velocity is 0. So here velocity is 0 and this is increasing as the slope is increasing up to point of inflection. So velocity will increase. Okay, point of inflection are the points where the nature of the curve changes. Okay, so from here the velocity will increase from 0 to point of inflection, and at point of inflection velocity will be maximum, and after these point the slope of the curve is decreasing and at the top of the band the slope is 0, so velocity will be decreasing, and at the top of the band velocity of the electron will be 0. Similarly, for negative direction the slope of the curve is increasing up to point of inflection. Okay, so the velocity will increase up to the point of inflection in negative direction, and after this slope is decreasing and velocity is 0, so this will decrease in negative direction and here the velocity will be 0. Now from equation number 2 we can find out the acceleration of the particle. So acceleration is a equal to dv by dt, and this is equal to 1 upon h cut d by dt into dE by dk. Okay, now here we can multiply and divide by dk upon dk. So we have acceleration equal to 1 upon h cut d2e upon dk square and dk upon dt. Now, this d2e upon dk square, this can be find out from E versus K diagram. This is obtained from E versus K diagrams. Now, we have to find out dk by dt by applying the electric field. Suppose an electric field is applied on the electron that is moving inside the crystal, and let that electric field is represented by J. I have taken the symbol J instead of E because E is representing here the energy. So we'll take the different symbol from the energy. So let an electron is accelerated in the electric field J for a time dt, and for that time v is the velocity. Now the distance traveled by the electron is v into dt. This will be distance traveled by the electron in field J. Okay. Now increase in energy, increase in energy, that is dE, will be given by force into displacement, force into displacement, and force in electric field is E into J, or simply we represent, if E is electric field, E into E. Here J is electric field, so E into J into what is displacement? Displacement is V into dt. This is displacement. Okay. Now dE equal to Ej, put the value of V 1 upon h cut dE by dk into dt. Multiply and divide by dk here. Dk into dk equal to Ej upon h cut dE by dk into dt. So this is cancelled out and we get dk upon dt equal to Ej upon h cut. Put the value of this dk by dt here. We have acceleration equal to 1 upon h cut d2 e upon dk square into Ej upon h cut. So we have 1 Ej upon h cut square into d2e upon dk square. This is acceleration. Now we can show that this acceleration is depending upon d2e by dk square. Now for free particle, we know acceleration is force upon mass. So this is Ej upon m. Now comparing these two equations, we have m and we will represent it by m star. M star equal to h cut square into d2e upon dk square inverse. If we compare these two equations, this is a common, and what is m? This is equal to h cut square upon d2e upon dk square. This is called effective mass of the electron. Mass of the electron. From this equation, we can also show that h cut into dk upon dt equal to Ej, and from here dh cut k upon dt equal to Ej. Now this h cut k is p, so dp upon dt equal to Ej. Now this force is equal to rate of change of momentum. This p is crystal momentum. Crystal momentum. Crystal momentum. Okay. Now this force is equal to dp by dt, and this is analogical to Newton's law. Now we will plot m star effective mass versus k diagram. Okay, we know effective mass is dependent on d2e upon dk square. Now, which can be find out from E versus K diagram. Now you can see that near the origin, or the at the bottom of the band, bottom of the brilliant zone, you can see this curvature is positive, or you can say this d2e upon dk square, this is positive. Okay, if curvature is positive, then you see this effective mass is positive in this region. Effective mass will be m star will be positive. Okay, up to point of inflection. Otherwise, in this region, you can see that this curve is similar to the curve for free particles. Free particle. So in this region, you can see, you can show that effective mass m star equal to m, or positive. So in this region, we can show effective mass will be positive. This is not zero. Effective mass of the electron cannot be zero. That's why this curve do not meet at zero. Effective mass cannot be zero. This is positive side. Okay. Now at point of inflection, this point of inflection cannot. At point of inflection, this d2e upon dk square, this will be 0. d2e upon dk square 0, because at this point the shape of the curve, or the nature of the curve is changing. So here curvature will be 0. If the curvature is 0, then from this relation, it means this m star is infinite. Effective mass is infinite. That's why this curve is approaching to infinity near this point of inflection. Okay, now if we see this portion from point of inflection to here, this portion, or you can say top of the band, upper portion of the band, in this portion, you can see clearly that curvature is negative, or you can say d2e upon dk square is negative. So m star will be negative. Effective mass is negative. That's why in this region we get the curve like this. again near this point of inflection, this curve is approaching to infinity. Okay, so in this region effective mass is negative, in upper portion effective mass is positive, and near the point of inflection effective mass is infinite. You can also show this, explain this curve with the help of this V versus K diagram. Now, what is the significance of this effective mass? Significance of positive, negative, and infinite effective mass. In positive region, we can show that this curve is similar to the free particle curve. Free particle curve where E equal to h cut square k square upon 2m up to this region k naught minus k naught and k naught. This is similar for the free particle curve. So in this region mass is positive and this effective mass will be same as the mass of free electron. Okay, now at point of inflection at this point you can see that this effective mass is approaching to infinity, this mass is approaching to infinity. So at point of inflection, point of inflections, or you can say k naught minus k naught and plus k naught, this effective mass approaches to infinity. Why this mass is infinite here? So we can explain it with the help of this periodic potential diagram. Okay, you can see from Cronin-Penny model that these are potential barriers. Okay, here potential is V naught, V naught. Here potential is 0. So when we apply the electric field and suppose the electron is moving in this direction, then electron will strike here. Okay, and there will be de Broglie wave, and that wave is associated with this electron, and this wave will be reflected from this potential barrier. So this will be Bragg reflection. Okay, now this reflected wave will have the same momentum as the forward wave. Okay, or you can say the wave which is obtained under the applied electric field. So these two momentums, one for Bragg reflection, Bragg's reflection, and other for forward movement of the electron. These two momentums are equal. When these two momentums are equal, then the electron will not move further. Okay, and that will behave like that it has infinite mass. This is having very much mass. This will be seems to be very high. That's why it is not going forward. Okay, so that's why m star effective mass is infinite. Third point is that effective mass is negative. So what is physical significance of this? What is physical meaning of this? Now we can see from here that in this case, when we are applying the electric field, then electron should move in this direction. But in this case, barrier strength is very high, and this barrier will reflect this electron very significantly. Okay, and this reflection, this Bragg's reflection will dominate over the forward motion of the electron. Or you can say this Bragg reflection, the momentum due to Bragg reflection will dominate over the momentum for forward motion of the electron. So this will pull the electron to the negative side. So it is assumed here that mass m star effective mass is negative. Okay, so this was the physical significance for positive, negative, and infinite effective mass. Now we will introduce another term, Fk equal to m upon m star, that is equal to m upon h cut square d2e upon dk square. This factor Fk is the extent up to which the electron is free in k state. This will give the extent up to which the electron is free in k state. If m star is large, then Fk will be small and the particle will behave as heavy particle. And when Fk equal to 1, Fk equal to 1, it means mass, effective mass will be equal to mass of the free electron. Plot of Fk versus k is shown here. Now this was all about the velocity of the electron and effective mass of the electron, that is mass of the electron inside the crystal under the electric field. Why it is different from the mass of the free electron, and we have shown the physical meaning of the positive, negative, and infinite effective mass. So this was all about the topic. Thank you very much.